Welcome to lecture 11, which is the further and inverse state transform, which is last lecture in signal and system. Okay, last lecture we talked about discrete signal processing and the state transform and the transfer function HC. And this week we are going to talk about the region of convergence and power series representation of the state transform and the inverse state transform. So firstly, there are several approaches to the state transform. Firstly, we can apply for the definition, which is the summation from 0 to infinity xn times z to the power of minus n, and difference equation from the Bloch diagram. And we can also do the state transform of a difference equation. And in lecture 11, we're going to talk about the transfer function from a block diagram Z, the power series, the Z transform table, and the partial fraction. So firstly, let's talk about continuous and discrete. For the continuous one, which is illustrated in the last lecture, the corresponding xt, yt, ht, Laplace, hs, and hs is as a transfer function. We're going to re-represent it as xn, yn, hn, z, hz, and hz. Okay, and time delay is just we're going to time. What if it is delayed by several samples? The corresponding z domain will be timed with z to the power minus a, and this is just an illustration. I think is that we don't know why it is minus. This is a very interesting part, because if we are delaying something, so let's see original signal is here, and the new signal, this one is delayed, right? Because time is going in that direction, so it's like a minus, because what if on the left is your plus, what if on the right your minus. That is basically minus. And so let's talk about the inverse Z transform. So the inverse Z transform is just like the inverse Z transform is just we apply the following formula, but it is worth noticing that generally we do not apply this formula directly. We are going to use the since it's too complex to be considered, we generally apply the table to do the inverse. And additionally, we're going to talk about the region of convergence, where it's like a region of Z, which the G transform convergence, where the norm of the Z is less than infinity, and the summation from 0 to infinity xn times the Z to the power of minus n, the norm of that is less than infinity. So the Z transform is for example, in this one, this equation, this is just like the equivalent multiplication series, where the in Chinese they call the 等差数列 and 求和公式。That it will have what if we want to have that kind of the convergence one, this kind of expression, we need to make sure the norm of Z is less than 0. The reason is that what if the reason why we can get this. What if it's the original form? What do we get? The thing is that let me tell you, and and A1 is 1, Q equals to X, Sn equals to An 1 times 1, just the therefore it's just 1 minus Q is X, A1 times 1 minus X for all. What if the X is less than 0? Then this one and is approaching to infinity. This one is going to be 0. So therefore we are going to it is when x is less than 0, less than 1, it will going to be 1 divided by x. So that is basically the and what if just the same thinking routine where it is ax when you're going to make sure the norm of ax is less than 1. So therefore the series only converges if the red one are true. So let's give an example. We are going to see the xn is to the a to the power of n times a to the power of n times un. The xn is just the summation from 0 to infinity xn to the power of z minus n. And in order to so let's just apply the xn there, and since the un is not necessary because we are going talking about one side of this one, so I only left with a to the power of n. Therefore, we're going to get the n outside, which is the norm is just a times z to the power minus 1. So I need to make sure a times z to the power minus 1, the norm of that is less than 1. So let's say z is greater than a norm. In this case, just like a is just like radius of the circle, and what if it's just the shade area? This is shade area outside this circle. So this is just how do we represent the radiance of convergence. So and this is all the J transform table is shown, just like what we illustrated. What if with and delta functions, x is 1, and what if it's a unit step, it is z divided by z minus 1. And one final thing we can talk about the partial fraction. Oh, the partial fraction in Chinese is called 列项 and then it's this one is not very this one is it's just like we can I see, we can change the dz to a summation of we can substitute the dz to a series of denominator and sum them up. For example, in this case is where we have the z plus 1 and z minus 1 as the denominator. We can see we can get 0.5 out of here, which is just like the coefficient, the parameters down there, which is 2 plus 2 is 1 plus 1 is 2, 1 divided by 2, and then we are going to apply each one for the corresponding formulas, and we're going to get the final answer for that. And additionally, for this one, we're going to see that we're going to find the inverse J transform based on that. So we can see that each of that is z to the minus 1, z to the power of minus 2, z to the power of minus 3. Therefore, we're going to just extract the z xn out. This one is 1, this one is 0.4, this one is 0.16, this one is 0.064. And another thing is we are going to calculate the xn for the following signal, and this it will the first thing we can, this is 二项展开式, and in English which is called the binomial expectation. And actually I do not know what is this, but the thing is that we can use the table to do that, because z divided by z plus 1 is just z divided by z plus 1 is this one where a equals to minus 1. So minus 1 to the power of n times un. The final answer is, just that. Okay. So let's talk about the inverse z transform for the transfer function hz equals to z divided by z to the power of 4z to the power of 2 plus 1, using the series expansions and using the partial fractions. That is just what if it is 4z divided by 2. This one will illustrate that in the future. Thank you very much.